280 million years after the Big Bang, nothing bright was supposed to exist. The universe should have been a dark expanse of neutral hydrogen, still assembling its first fragile structures from formless gas. Then the James Webb Space Telescope captured light that had travelled over 13 billion years and revealed something that should not have been there. A galaxy. Compact, luminous, already laced with nitrogen, an element that demands multiple generations of stellar chemistry to produce. This was not a single anomaly. Webb keeps finding bright galaxies across the earliest observable epoch, appearing roughly 100 times more often than the best models predicted. The first few 100 million years of cosmic history were not empty. They were already becoming complicated, and no one fully understands why. If this kind of deep space storytelling grabs you, I would really appreciate it if you took a second to hit that like button and subscribe. It helps more than you know, and there is so much more to explore together. Now, settle in and get yourself comfortable. Let's begin. Everything you have ever seen in the night sky is old. Not old in the way a museum artifact is old in a way that dismantles your sense of the present moment entirely. Light travels at a finite speed, roughly 186,000 miles per second, and even at that blistering velocity it requires time to cross the distances between cosmic objects. The light from our nearest stellar neighbour, Proxima Centauri, takes 4 years and 3 months to reach Earth. You are not seeing that star as it exists right now. You are seeing it as it was when the light left its surface, over 4 years ago. This delay is trivial at close range, but stretch the principle across billions of light years and it becomes something else entirely. It becomes a time machine. When astronomers point a telescope at a galaxy 1 billion light years away, they are not observing that galaxy in the present. They are seeing it as it existed 1 billion years ago, when the light they are collecting first began its journey across expanding space. Point the telescope at a galaxy 5 billion light years away, and you see the universe as it looked when our own solar system had not yet formed. Point it at 10 billion light years, and you are watching galaxies that existed when the universe was less than a third of its current age, young, chaotic, still assembling themselves through violent collisions and rapid bursts of star formation. Every increase in distance is an increase in look-back time. The farther you peer, the deeper into history you reach. The sky is not a static photograph. It is a layered archive of cosmic history, with the most ancient chapters written in the faintest, most distant light. And this is not a limitation. It is one of astronomy's greatest tools. Because light takes time to travel, every observation of a distant object is also an observation of the past. A telescope is not merely a magnifying instrument. It is a device for recovering lost time. And the more powerful the telescope, the further back in time it can recover. Push far enough, to the most extreme distances modern instruments can detect, and you are looking at the universe when it was barely old enough to contain anything recognizable. You are watching the cosmos in its infancy. This is what makes the James Webb Space Telescope so extraordinary. It was not built merely to see farther than its predecessors. It was built to see earlier. Its primary mirror, 6.5 meters across, and coated in a microscopically thin layer of gold optimized for infrared reflection, collects light with a sensitivity that surpasses anything previously deployed in space. Its 4 science instruments were designed from the ground up to detect the faintest, most ancient photons still traveling through the cosmos, light that has been stretched by the expansion of the universe from its original ultraviolet and visible wavelengths deep into the infrared. Webb orbits the second Lagrange point, roughly 1.5 million kilometers from Earth, shielded from solar and terrestrial heat by a sunshade the size of a tennis court. From that vantage point, cooled to temperatures approaching -230 degrees Celsius, its detectors can register individual photons that left their sources more than 13 billion years ago. Webb is, in a very real sense, an archaeological instrument. Every photon it catches carries a timestamp from a distant cosmic era, and when it began its science operations in July of 2022, it started digging into epochs that no telescope had ever clearly seen. To understand why the galaxies Webb has found are so troubling, you first need to understand what astronomers mean when they talk about redshift. The concept sounds technical, but its core idea is surprisingly intuitive. The universe is expanding, not in the way an explosion scatters debris outward from a central point, but in the way the fabric of space itself stretches in every direction simultaneously. Galaxies are not flying through space away from each other. The space between them is growing, and as that space grows, it stretches everything traveling through it, including light. Imagine a wave of light leaving a distant galaxy 13 billion years ago. As that wave crosses the cosmos, the expansion of the universe gradually stretches its wavelength. A shorter wavelength, which our eyes would perceive as blue or ultraviolet, gets pulled toward longer wavelengths. It shifts toward the red end of the spectrum. This is redshift. The greater the distance the light has traveled, the more the universe has expanded during its journey, and the higher the redshift value. Think of it like a rubber band with a wave drawn on it in ink. When you stretch the band, the wave stretches with it. The peaks move farther apart. The wavelength increases. Cosmic expansion does exactly the same thing to every photon traveling through it, continuously, relentlessly, across billions of years. A photon that began as ultraviolet light can arrive at a telescope as infrared light, its wavelength stretched tenfold or more by the cumulative expansion of all the space it crossed. Astronomers assign a number to this stretching. A redshift of 1 means the light's wavelength has been doubled since it was emitted. A redshift of 2 means the wavelength has tripled. A redshift of 10 means the wavelength has been stretched by a factor of 11. At redshift 14, the light arriving at Webb's detectors has been stretched by a factor of approximately 15. The original ultraviolet glow of young stars has been pulled so far into the infrared that it is completely invisible to any optical telescope ever built. It can only be detected by an instrument specifically designed to see in infrared wavelengths, which is exactly what Webb is. But redshift is more than a measure of wavelength stretching. Because the expansion of the universe has been occurring since the Big Bang, redshift also serves as a cosmic clock. A higher redshift corresponds to an earlier moment in the history of the universe. A galaxy at redshift 1 existed when the universe was roughly 6 billion years old. A galaxy at redshift 6 existed when the universe was less than 1 billion years old. A galaxy at redshift 10 existed when the universe was roughly 500 million years old, a small fraction of its current lifespan. And a galaxy at redshift 14 existed when the universe was approximately 280 million years old, barely 2% of its present age of 13.8 billion years. At that redshift, you are not simply looking at something far away. You are looking at the cosmos during a period so early that most models predicted there would be almost nothing there to see. And here is where the story becomes unsettling. The universe at that age was not supposed to contain bright galaxies. Not yet. Not already. To understand why, you need to follow the sequence of events that unfolded after the Big Bang. In the first few minutes, the universe was a blinding soup of subatomic particles and radiation, hot enough for nuclear fusion to occur throughout all of space. Protons and neutrons collided and merged, forging the lightest elements: hydrogen, helium, and trace amounts of lithium. No heavier elements existed. Carbon, oxygen, nitrogen, iron, every element that would eventually form planets and living things, none of it had been created. Then the universe cooled. For roughly 380,000 years, it remained a dense fog of ionized gas, so thick with free electrons that photons could not travel more than a short distance before scattering off in a random direction. Light was trapped. The universe was opaque, a glowing wall of plasma in every direction. Then came a moment called recombination. The temperature dropped to roughly 3,000 degrees, and for the first time, electrons could bond with protons to form stable neutral hydrogen atoms. With the free electrons swept up into atoms, the fog cleared. Photons were released to travel freely through space for the first time in cosmic history. That ancient light, stretched over 13.8 billion years from its original glow into faint microwave wavelengths, is what we detect today as the cosmic microwave background, the afterglow of the Big Bang, that fills the entire sky at a temperature of approximately 2.7 degrees above absolute zero. It is the oldest light in the universe, and it marks a boundary. Everything beyond it, everything earlier, is hidden from electromagnetic observation. After recombination, the universe entered a period that astronomers call the Cosmic Dark Ages, And the name is not poetic license, it is literal. There were no stars, no galaxies, no luminous sources of any kind anywhere in the entire cosmos. Space was filled with neutral hydrogen and helium gas, cooling slowly as the universe expanded. If you could somehow transport yourself to that epoch and open your eyes, you would see nothing. Perfect, absolute darkness in every direction. No pinpoints of starlight, no glowing nebulae, no faint haze of distant galaxies, just a featureless void of cold gas stretching beyond comprehension. But the universe was not idle during this darkness. Gravity was doing its work, quietly and relentlessly. Dark matter, the invisible scaffolding that outweighs ordinary matter by roughly 5-1, had already begun pulling itself into denser clumps and elongated filaments, creating the skeletal framework of what would eventually become the cosmic web of galaxies, clusters, and superclusters. Ordinary matter, the hydrogen and helium gas, drifted within this dark matter framework, slowly settling into the gravitational wells being carved out for it. But the gas had not yet reached the densities and temperatures needed to trigger gravitational collapse into stars. The ingredients for galaxies were assembling, but the recipe had not yet been completed. The universe was preparing, not performing. This darkness lasted for tens of millions of years. Some theoretical models suggest it persisted for more than 100 million years, possibly 150 million or longer, before the very first stars ignited. Those first stars, referred to by astronomers as population 3 stars, would have formed from pristine hydrogen and helium gas, containing none of the heavier elements that later generations of stars would inherit from the debris of their predecessors. They are predicted to have been enormous, potentially hundreds of times the mass of our Sun, burning through their nuclear fuel at a ferocious pace. Their surfaces would have blazed at temperatures far exceeding those of modern stars, pouring ultraviolet radiation into the surrounding neutral gas and beginning the slow process of reionizing it. When these massive first stars died, they exploded in powerful supernovae that scattered the first heavy elements, carbon, oxygen, silicon, iron, into the surrounding interstellar medium. For the first time in the history of the cosmos, the raw materials for rocky planets and complex chemistry existed. But even after the first stars appeared, the process of building anything resembling a galaxy required additional time. Gas had to cool further and condense within dark matter halos. Those halos had to grow through mergers, combining smaller clumps into larger ones. The enriched debris from dead stars had to mix with fresh gas and collapse again. A second generation of stars had to form from that enriched material, and then a third. Galaxies were expected to emerge gradually, piece by piece, over hundreds of millions of years, through a slow accumulation of mass, repeated cycles of star formation and death, and the gradual merging of smaller structures into larger ones. The standard picture of cosmic dawn was not an instantaneous sunrise. It was a slow, patchy brightening, like scattered campfires appearing one by one across an enormous dark landscape. The first galaxies were expected to be small, faint, and exceedingly rare. Luminous galaxies, the kind that shine brightly enough to be detected across 13 billion light-years, were expected to take significantly longer to assemble. Most models built before Webb launched predicted that the universe at redshift 14 would contain almost nothing detectable. A few dim proto-galaxies, perhaps. Maybe the faintest traces of star formation beginning in the densest pockets of collapsing dark matter, but nothing bright, nothing chemically enriched, nothing that looked like a functioning galaxy already processing heavier elements at rates comparable to structures hundreds of millions of years older. Think about the timeline in concrete terms. The Big Bang occurred 13.8 billion years ago. The cosmic microwave background was released at roughly 380,000 years. The Dark Ages stretch from that point until somewhere around 100 to 200 million years later, when the first stars are thought to have formed. A galaxy detected at redshift 14 is being observed as it existed approximately 280 million years after the Big Bang. That leaves an astonishingly narrow window for the entire chain of events leading to a detectable galaxy to unfold. Depending on when the first stars actually ignited, that window may have been as short as 80 million years, perhaps 150 million at the generous end. To put that in perspective, 150 million years ago on Earth, dinosaurs dominated the land. Flowering plants were just beginning to diversify, and the Atlantic Ocean was still a narrow channel between separating continents. That is not a long time by cosmic standards, and within a window that short, the early universe had to accomplish a sequence that astronomers once assumed would take far longer. The gravitational collapse of dark matter into sufficiently massive halos, the cooling and condensation of gas within those halos, the ignition and death of the first generation of massive stars, the chemical enrichment of the surrounding gas with heavier elements, the formation of subsequent stellar generations from that enriched material, and the accumulation of enough starlight in one location to make a galaxy visible across 13 billion light-years of expanding space. Every link in that chain requires time, and the universe at redshift 14 had barely any to offer. Detecting objects at these extreme distances required not just a powerful telescope, but a specific observational strategy. Webb's primary imaging camera, NIRCam, observes in multiple infrared filters spanning wavelengths from roughly 0.6 to 5 micrometers. When astronomers image a deep field through these filters, most galaxies appear in all of them. But a galaxy at very high redshift produces a distinctive signature. The neutral hydrogen that fills intergalactic space during and after the cosmic dark ages absorbs virtually all light at wavelengths shorter than the Lyman alpha line, a specific ultraviolet transition of hydrogen at a rest wavelength of 1,216 angstroms. For a galaxy at redshift 14, this absorption edge is shifted to approximately 1.8 micrometers in the observer's frame. The galaxy vanishes completely in every filter below that wavelength, and appears only in the longer wavelength filters, as if someone had drawn a curtain across the blue half of the spectrum. This disappearing act is called a Lyman break dropout. The galaxy drops out of the short wavelength images as though it does not exist, while remaining clearly visible in the redder filters. Astronomers photograph the same region of sky through a sequence of filters and search for objects that follow this precise pattern. The specific filter where the dropout occurs indicates the approximate redshift. A galaxy that drops out around 1.5 micrometers but remains visible at 2 is likely near redshift 11 or 12. A galaxy that drops out even at 1.8 micrometers and appears only beyond 2 micrometers is a candidate for redshift 14 or higher. But photometric dropout selection alone is not sufficient to confirm a galaxy's distance. Other types of objects can mimic the dropout signature. A dusty galaxy at a much lower redshift might also appear faint or invisible in short wavelength filters due to dust absorption rather than Lyman alpha absorption. A cool brown dwarf star in our own Milky Way could produce a confusingly similar color pattern. Photometric misidentification has tripped up astronomers before, and at the highest redshifts, where candidates are faint and rare, the risk of contamination is significant. To confirm that a dropout candidate is genuinely at extreme redshift, astronomers need spectroscopy. Webb's NIRSpec instrument disperses the collected light from a target across its component wavelengths, producing a detailed spectrum. In that spectrum, the Lyman alpha break appears as a sharp cliff, a sudden drop to zero flux at a specific wavelength. Emission lines from ionized gas within the galaxy appear as bright spikes at positions determined by atomic physics. The precise wavelengths of those features lock in the redshift, removing all ambiguity. A confirmed spectroscopic redshift is the gold standard of distance measurement in extragalactic astronomy. This two-step process, photometric candidate selection, followed by spectroscopic confirmation, is the method that produced the current distance record holders. It is painstaking work, requiring hours of exposure time per target and meticulous analysis to distinguish genuine detections from instrumental noise, background fluctuations, and systematic artifacts. But when a galaxy passes both tests, the result is definitive. The object is real, its distance is confirmed, and if that distance corresponds to a time when the universe should have been nearly empty, the questions that follow are not trivial. Webb was designed to find the first galaxies. That was one of its 4 core science objectives, embedded in the mission from the earliest planning stages in the 1990s. The expectation was that it would detect a small number of faint, tiny galaxies at the very edge of the detectable epoch, offering tantalizing but limited glimpses into the opening moments of cosmic dawn. The telescope exceeded that expectation so dramatically that it forced a rethinking of early universe models within its first year of science operations. Multiple independent survey programs contributed to the emerging picture. The JWST Advanced Deep Extragalactic Survey, known as JADES, targeted two of the most intensively studied deep fields in the sky, combining deep NIR-CAM imaging with extensive NIR-SPEC spectroscopy to identify and confirm high redshift galaxies with unprecedented depth and precision. The Cosmic Evolution Early Release Science Program, SEERS, provided wide-area imaging that captured bright high redshift candidates across a larger volume of cosmic space. The Cosmos Web Survey covered an even broader field, assembling a statistical census of luminous early galaxies across a sky area more than 100 times larger than the Hubble Ultra Deep Field. Additional programs like GLASS used the gravitational lensing effect of massive foreground galaxy clusters to magnify background objects, reaching intrinsically fainter and smaller galaxies at extreme distances that would otherwise be undetectable. Each of these programs independently reported the same unsettling result. There were far more bright galaxies at high redshift than anyone had anticipated. Not slightly more. Not within the margin of uncertainty. In some redshift ranges above 10, the number of luminous galaxies exceeded pre-Webb predictions by factors of 10 to more than 100. The ultraviolet luminosity function, the statistical tool that describes how many galaxies exist at each brightness level for a given cosmic epoch, showed a much shallower decline toward higher redshifts than any pre-launch theoretical model had forecast. Instead of dropping steeply as the clock wound back toward the Dark Ages, the galaxy counts remained stubbornly high. Bright galaxies were not vanishing as astronomers peered deeper into the past. They were persisting, scattered across the earliest observable era in numbers that the standard framework simply had no room for. The initial reaction within the astronomical community was appropriate scientific caution. Early photometric samples could have been contaminated by low redshift interlopers masquerading as distant objects. Systematic errors in photometric redshift estimation could have inflated the apparent count of high redshift candidates. But as spectroscopic follow-up campaigns confirmed candidate after candidate over the course of 2023 and 2024, the pattern held firm. Interlopers existed, but they were the minority. The majority of candidates turned out to be genuine high redshift galaxies. A spectroscopic confirmation at redshift 12 was followed by another at 13, then a pair at redshift near 14. The previous record holder before Webb, a galaxy called GNZ11, originally discovered by Hubble and later measured at redshift 10.6 by Webb's own NIRSPEC, was surpassed repeatedly. By mid-2025, the spectroscopic frontier had been pushed to redshift 14.44. The bright early galaxies were real. They were confirmed, and there were far more of them than any model built before Webb's launch had predicted. The question was no longer whether luminous galaxies existed during the first few 100 million years of cosmic history. They did, and the evidence was beyond dispute. The question had become sharper and more urgent. Why were these galaxies so luminous when the universe had barely begun? Why were there so many of them when models expected almost none? Why did some already carry chemical signatures that should have required far more time to develop? And if the standard picture of early galaxy formation was this far off, what exactly had it gotten wrong? The answers depend on the specific objects that now define the frontier. Two galaxies in particular, both spectroscopically confirmed at redshifts above 14, carry the most weight. One of them, JADES-GS-z14-0, was already a landmark when it was confirmed in early 2024, shattering the distance record and revealing a galaxy so luminous that it challenged the most optimistic formation scenarios. The other, MoM-z14, arrived even further back in time and brought with it chemical signatures that made the mystery not merely stranger but measurably more difficult to explain. Together, they represent the sharpest confrontation between observation and expectation that the early universe has produced. Their ancient light has been travelling for more than 13 billion years, and the story it carries refuses to fit neatly into the framework that was supposed to explain it. The galaxy that rewrote the record books arrived not with a dramatic announcement, but with a careful, painstaking process of elimination. In October of 2023 and January of 2024, Astronomers working on the JWST Advanced Deep Extragalactic Survey used Webb's NIRSpec instrument to collect spectra of faint dropout candidates identified in deep NIRCam imaging of the Good South Field. One of those candidates had been flagged months earlier as a potential high redshift galaxy, but it carried an asterisk. By coincidence, it sat at a projected distance of only 0.4 arcseconds from a foreground galaxy at a much lower redshift, and the foreground object's spectral features landed at wavelengths suspiciously close to the photometric break that made the candidate look distant. Some analysts initially dismissed it as a low redshift interloper with an unusual spectral energy distribution. Others were not so sure. Additional medium-band NIRCam observations from the JADES Origins field program strengthened the case for a high redshift interpretation, and the team pushed forward with spectroscopy to settle the debate. When the spectrum came back, the debate ended. The flux dropped to zero below approximately 1.8 micrometers, producing a sharp Lyman alpha break with no ambiguity. The object was not a confused foreground galaxy. It was a genuine galaxy at the edge of observable cosmic history. The team, led by Stefano Carniani, published the result in Nature in mid-2024. The initial spectroscopic redshift from the NIRSpec prism was approximately 14.32. Subsequent observations with the Atacama Large Millimeter Array, ALMA, detected emission from doubly ionized oxygen at 88 micrometers, an emission line that had never been detected at such an extreme distance. The ALMA detection refined the redshift to 14.1793, plus or minus 0.0007. The galaxy had a name that sounded more like a catalogue entry than a headline, JADES-GS-z14-0, but its properties made headlines inevitable. Start with its brightness. JADES-GS-z14-0 has an absolute ultraviolet magnitude of approximately negative 20.81. That number, for anyone outside professional astronomy, means almost nothing in isolation. So consider what it implies. Among all galaxies ever spectroscopically confirmed above redshift 8, only one, GN-z11, at redshift 10.6, is more luminous. JADES-GS-z14-0 is not a dim flicker at the edge of detectability. It is a beacon. Its ultraviolet output places it among the brightest galaxies in the entire observable volume of the early universe, outshining the vast majority of objects at comparable or even substantially lower redshifts. For a galaxy that existed fewer than 300 million years after the Big Bang, that luminosity is startling. It implies a rate of star formation and a quantity of hot young stars that most formation models had not predicted for that epoch. Now consider its size. The galaxy is spatially resolved in Webb's imaging, meaning it is not a point source like a star or a compact active galactic nucleus. Its half-light radius, the distance from the center within which half of its total light is contained, measures approximately 260 parsecs, plus or minus 20. That is small by the standards of a modern galaxy like the Milky Way, whose disk spans tens of thousands of parsecs. But it is large enough to demonstrate that the ultraviolet emission is produced by a distributed population of stars and surrounding ionized gas, not by a single accreting supermassive black hole dominating the output. The light from JADES-GS-z14-0 is starlight. It comes from an actual galaxy, a collection of stars burning in a compact but spatially extended structure, operating as a coherent star-forming system less than 300 million years into cosmic history. The ALMA detection added a dimension that imaging alone could not provide. Doubly ionized oxygen requires oxygen to exist, and oxygen is forged exclusively inside stars through nuclear fusion and released into the interstellar medium when those stars die. Detecting oxygen emission at redshift 14 means that stars within this galaxy had already lived, fused heavier elements in their cores, exploded or shed their outer layers, and enriched the surrounding gas with their debris. The chemical cycle of stellar birth, nuclear processing, death, and enrichment had already completed at least one full turn, possibly more, within the first 300 million years. The galaxy was not just forming stars, it was already recycling them. Then came the MIRI detection. Webb's mid-infrared instrument observed the galaxy at 7.7 micrometers, a wavelength that probes rest frame optical light at this redshift. The detection, reported in a first author publication by Jakob Helton in Nature Astronomy, provided additional constraints on the galaxy's stellar mass and its history of mass assembly. The results suggested that a significant amount of stellar material had already been built up in a remarkably short period. Not billions of solar masses, but enough to show that the galaxy had been forming stars at a sustained, vigorous pace for much of its short existence. The galaxy was not a momentary flash. It had depth, history, accumulated weight. Each of these properties, the luminosity, the resolved spatial extent, the oxygen emission, the infrared detected stellar mass, individually challenged pre-Webb expectations for what a galaxy at redshift 14 should look like. Together, they painted a picture that was difficult to reconcile with the slowest and most conservative formation timelines. JADES-GS-z14-0 was not a marginal detection. It was a fully operational galaxy, compact but real, bright but star-dominated, chemically active but barely 300 million years old. Finding it was like arriving at a construction site where only a foundation should have been poured and discovering a furnished house with the lights on. When astronomers absorbed the implications, the conversation shifted. The question was no longer whether galaxies could exist at redshift 14. One clearly did. The question became whether JADES-GS-z14-0 was a singular freak, a 1 in a trillion statistical outlier that happened to land in Webb's field of view, or whether it was a representative member of a population that the old models had simply failed to predict. The answer did not arrive all at once. It accumulated over the months following JADES-GS-z14-0's publication, as other spectroscopic campaigns continued confirming high redshift galaxies at progressively more extreme distances. Each new confirmation was individually less dramatic than the redshift 14 record, but collectively, they were building a case that no single outlier could explain. Through late 2024 and into early 2025, near-spec programs across multiple survey fields kept returning the same pattern. Galaxies at redshift 11 confirmed. Galaxies at redshift 12 confirmed. A growing handful at redshift 13, each one spectroscopically verified through emission lines and Lyman alpha breaks that left no room for misidentification. The previous distance frontier, which had stood at redshift 10.6 with GNZ11 for years before Webb launched, was not just surpassed once by JADES-GS-z14-0, it was surpassed repeatedly by multiple objects in multiple fields observed by multiple teams. The spectroscopic frontier was not a single spike driven by one lucky observation in one deep field. It was a rising tide across the entire observational landscape. More telling than the record breakers were the galaxies just below them. Objects at redshifts of 11, 12 and 13 were appearing with properties that matched the pattern JADES-GS-z14-0 had established. Compact morphologies, high ultraviolet luminosities, and in several cases, emission line detections indicating that chemical enrichment was already underway. These were not headline-grabbing discoveries individually. No single galaxy at redshift 12 generates the same attention as a confirmed detection at redshift 14, but they were filling in the space between the record holders and the well-studied galaxy populations at lower redshifts, demonstrating that the abundance excess was not a phenomenon confined to one extreme data point. It extended continuously across the redshift range from 10 to 14, growing more pronounced at higher redshifts, where the predictions had been most confident that few galaxies would exist, and beneath the confirmed detections, the photometric candidate lists were growing even faster. NearCam imaging from Cosmos Webb, JADES and other programs continued accumulating dropout objects whose colours suggested redshifts of 12, 13, 14 even beyond. Most of these candidates had not yet been observed spectroscopically. They sat in catalogues as statistically compelling, but individually unconfirmed, their photometric redshifts carrying the unavoidable uncertainty that comes from inferring distance through broadband colours alone, but their sheer numbers were becoming difficult to dismiss. If even half of them were genuine, the abundance of bright galaxies at extreme redshifts was not a marginal excess. It was a systematic feature of the early universe that demanded explanation. The situation created a specific scientific pressure that went beyond the usual cycle of discovery and follow-up. The community did not merely need more galaxies confirmed at high redshift to improve statistics. It needed a targeted, deliberate spectroscopic test of the brightest and most provocative candidates, the objects whose photometric redshifts placed them at the most extreme distances and whose luminosities were the most challenging for formation models to accommodate. These were the candidates most likely to be photometric mirages if systematic errors in the dropout technique were inflating the apparent excess. And they were the candidates whose confirmation would carry the most scientific weight if they turned out to be real, because they would demonstrate that the tension between observation and theory persisted at the very brightest luminosities where model predictions were most definitive. That pressure led directly to the design of a dedicated James Webb NIRSpec spectroscopic campaign targeting exactly these objects. The program selected the most luminous dropout candidates from Cosmos Webb and other wide-area imaging surveys, objects that sat at the statistical extremes of what photometric selection had produced, and allocated precious telescope time specifically to obtain their spectra. The goal was explicitly diagnostic rather than exploratory. It was not a search for new candidates, it was a test of existing ones. Confirm them or reveal them as interlopers, and in doing so determine whether the bright end of the early galaxy population was a genuine feature of the cosmos or an artifact of systematic photometric contamination at the detection frontier. The survey's name captured the binary nature of the question it was designed to answer. MoM-z14 takes its name from the survey that found it. Mirage or Miracle? A dedicated James Webb NIRSpec spectroscopic campaign designed to resolve exactly the kind of ambiguity that had initially clouded JADES-GS-z14-0. The survey targeted luminous high redshift candidates previously identified in Cosmos Webb and other imaging programs, objects whose photometric colors suggested extreme redshifts, but whose confirmations required spectroscopy. The name encoded the program's central question: were these bright dropout candidates genuine high redshift galaxies, cosmic miracles demanding new explanations, or were they photometric mirages, lower redshift objects masquerading as distant ones through coincidental color patterns? MoM-z14 turned out to be no mirage. In April of 2025, NIRSpec observations captured its spectrum. The data, led by Rohan Naidu and published first as a preprint and then formally in the Open Journal of Astrophysics in January of 2026, confirmed the galaxy at a spectroscopic redshift of 14.44, plus or minus 0.02. The spectrum showed not only the expected Lyman alpha absorption break, the sharp drop to zero flux below approximately 1.8 micrometers, but also 5 distinct ultraviolet emission lines, 5 separate atomic fingerprints, each appearing at a wavelength consistent with the same redshift, locking the measurement into place with a precision that left no room for misidentification. When a forensic investigator finds a single fingerprint at a crime scene, it is suggestive. When 5 prints from the same hand appear in the same room, the case is closed. MoM-z14 was confirmed. Its light left when the universe was approximately 280 million years old. It is, as of mid-2026, the most distant spectroscopically confirmed galaxy in the observable universe. But the redshift alone, while record-breaking, is not the most scientifically significant aspect of MoM-z14. Distance records are milestones, not revelations. What makes this galaxy genuinely troubling are the details encoded in its spectrum and its physical properties, details that carry implications extending far beyond a number on a distance chart. Begin with its brightness. MoM-z14 has an absolute ultraviolet magnitude of approximately negative 20.2, slightly less luminous than JADES-GS-z14-0, but still extraordinarily bright for its epoch. The Naidu team placed this luminosity in context by comparing it to the predictions of pre-Webb galaxy formation models. They found that the abundance of bright galaxies at these extreme redshifts exceeds those predictions by more than a factor of 100. Not a modest discrepancy. Not a factor of 2 or 3 that could be absorbed by tweaking a single parameter. 100-fold excess across multiple surveys, confirmed spectroscopically in multiple independent programs. The early universe did not produce a single improbable galaxy. It produced a population of them. Now consider the compactness. MoM-z14 is extremely small, with a circularized half-light radius of approximately 241 parsecs. For comparison, the distance from our solar system to the nearest star, Proxima Centauri, is approximately 1.3 parsecs. The entire visible half-light region of MoM-z14, containing a substantial fraction of its total stellar output, spans a volume smaller than the distance between our Sun and the nearest neighbouring star system multiplied roughly 185 times. This is a galaxy, but not in the sprawling sense we associate with modern spiral structures. It is a dense knot of star formation compressed into a tiny volume, pouring out ultraviolet light with an intensity that implies either an enormous number of stars crammed into a small space, or a smaller number of extraordinarily luminous stars dominating the output, or some combination of both. The ultraviolet spectral slope, measured as a parameter called beta, comes out at -2.5 plus or minus 0.2. This steep blue slope indicates that the galaxy contains very little dust. Dust absorbs and reddens ultraviolet light, and its absence here suggests that MoM-z14 is being seen in a relatively pristine state, its young stars shining through gas that has not yet been significantly polluted by the products of multiple generations of stellar death. The galaxy is bright not because dust is absent and we happen to see more of the light, but because the intrinsic ultraviolet production from its stellar population is genuinely powerful. The negligible dust is consistent with a very young stellar population that has not yet had time to build up significant quantities of solid particulate debris from supernovae and stellar winds. And then there is the nitrogen. This is where MoM-z14 crosses from remarkable into deeply puzzling. Among the 5 emission lines detected in its spectrum, one comes from nitrogen. The measured nitrogen to carbon abundance ratio is greater than 1, with values estimated between 1.3 and 1.7, corresponding to more than 10 times the solar nitrogen to carbon ratio. That is an extraordinary number. In the standard picture of chemical evolution, nitrogen is not a straightforward product of the earliest stellar generations. Carbon and oxygen are produced directly by massive stars and released by supernovae. Nitrogen, by contrast, is primarily manufactured through a slower process called the CNO cycle, in which carbon and oxygen already present in a star's interior serve as catalysts for hydrogen fusion. The bottleneck reaction in this cycle preferentially converts existing carbon and oxygen into nitrogen, but the process requires that carbon and oxygen be present in the star from the start, meaning the gas from which the star formed must already have been enriched by a previous generation of stellar deaths. Nitrogen enrichment on this scale is not something that happens in the first generation of stars. It requires prior chemical processing, recycling, and accumulation. Finding this level of nitrogen enrichment in a galaxy only 280 million years after the Big Bang forces an uncomfortable question. How did the chemical recycling happen so fast? The standard timeline barely allows enough time for 1 or 2 generations of stars to live and die, let alone for the complex nucleosynthetic chain required to produce supersolar nitrogen abundances. Something accelerated the process, and the spectrum offers a clue about what that something might be. The NIDU team noted that the nitrogen-to-carbon pattern in MoM-z14 closely resembles abundant signatures observed in a very specific class of objects in the nearby universe, ancient globular clusters in the Milky Way. Globular clusters are dense, compact collections of stars, many of which formed within the first 1 or 2 billion years of cosmic history. For decades, astronomers have puzzled over the fact that stars within these clusters show unusual light element abundance patterns, including elevated nitrogen, that do not match the standard chemical evolution expected for their age and metallicity. One leading explanation is that the earliest generations of stars in these clusters included very massive objects, possibly in the range of hundreds or even thousands of solar masses, whose extreme internal temperatures drove the CNO cycle at a ferocious rate, converting carbon and oxygen into nitrogen far faster than normal stellar populations could manage. These hypothetical supermassive stars would have burned through their fuel quickly and released their processed material into the surrounding gas, enriching it with nitrogen before the next generation of stars formed from that gas. If this interpretation is correct, MoM-z14 may be showing astronomers the formation environment of globular cluster progenitors in real time. The supersolar nitrogen to carbon ratio, the extreme compactness, the intense star formation rate, all of these properties are consistent with a dense, massive stellar nursery where supermassive stars could have formed, burned, and enriched the surrounding medium within the narrow window of time available. The chemical fingerprint connecting MoM-z14 to the Milky Way's oldest globular clusters would span the entire sweep of cosmic time, linking the most ancient stars in our own galaxy to a formation epoch now directly visible at redshift 14. This is an interpretation, not a confirmed conclusion. The data are consistent with it, but other explanations remain possible, including contributions from rapidly rotating massive stars, binary star interactions, or exotic stellar populations that have not yet been fully modelled. The nitrogen detection is firm. The production mechanism is still under investigation. The spectrum revealed one more surprise, and it concerns not the galaxy itself but the gas surrounding it. The Lyman alpha absorption feature in MoM-z14 spectrum shows a surprisingly weak damping wing. In simple terms, when light from a galaxy at this redshift passes through the intergalactic medium, the neutral hydrogen filling the space between galaxies absorbs photons near the Lyman alpha wavelength and produces a broad absorption trough called a damping wing. The strength of this wing depends on how much neutral hydrogen the light encountered along its path. At a redshift of 14.44, virtually every model of cosmic reionization predicts that the intergalactic medium should be nearly 100% neutral. The Dark Ages may have ended in terms of the first stars appearing, but the vast majority of intergalactic hydrogen at this epoch should not yet have been ionized by ultraviolet radiation. The damping wing should be strong, broad, and unmistakable. But in MoM-z14, the damping wing is weaker than expected. This provides tentative evidence that the immediate surroundings of the galaxy may be at least partially ionized. Something, whether MoM-z14 itself or other nearby luminous sources, has already begun carving an ionized bubble in the neutral intergalactic medium at a redshift, where the cosmos is supposed to be almost entirely opaque. Reionization, the global process by which the universe transitioned from neutral to ionized gas, was expected to begin in earnest around redshift 10 to 12 and conclude around redshift 6. Finding evidence of local ionization at redshift 14 pushes the opening act of reionization earlier than most models accommodated. The galaxy is not just forming stars and producing heavy elements ahead of schedule. It is also altering the state of the gas around it, contributing to a cosmic phase transition that was supposed to come later. Step back and consider what these two galaxies, JADES-GS-z14-0 and MoM-z14, represent when taken together. They are not just distance records. They are detailed physical portraits of the early universe that contain far more information than a single redshift number could convey. JADES-GS-z14-0 demonstrated that a luminous, spatially resolved, oxygen-enriched galaxy could exist at redshift 14, star-dominated and chemically active, within 300 million years of the Big Bang. MoM-z14 pushed the frontier slightly further in redshift, but substantially further in physical detail, adding the nitrogen enrichment puzzle, the connection to globular cluster formation, and the evidence for early ionization of the surrounding intergalactic medium. Neither galaxy should be described as impossible. That word gets thrown around too loosely in popular accounts of these discoveries, and it distorts the actual scientific situation. These galaxies exist. They have been observed. Their spectra have been measured. Their redshifts have been confirmed through multiple independent lines of evidence. They are not impossible. They are unexpected. The difference matters enormously. Calling something impossible implies that the laws of physics have been violated, that the fundamental framework of cosmology has collapsed, that scientists are confronting a crisis with no path forward. That is not what is happening. What is happening is that the specific models of how quickly galaxies could assemble, how efficiently gas could be converted into stars, and how rapidly chemical enrichment could proceed in the first few 100 million years, those models were calibrated on data that did not extend to these redshifts, and they underestimated what the early universe was capable of producing. The physics is not broken. The timeline is tighter than assumed. The efficiency is higher than predicted. The early universe accomplished more, faster, than the default expectations allowed. This distinction between impossible and unexpected is not a minor rhetorical point. It is the difference between a crisis that demands the abandonment of established physics and attention that demands the refinement of specific astrophysical models within a framework that still works. Lambda CDM cosmology has passed observational test after observational test across the full breadth of the observable universe. It is not what these galaxies threaten. What they threaten are the specific astrophysical assumptions built on top of that cosmological foundation to predict what the earliest galaxy populations should look like. Assumptions about how quickly gas turns into stars, how massive the first stellar generations were, and how efficiently feedback regulated early formation. Those assumptions were reasonable extrapolations from lower redshift data. They turned out to be too conservative. The models need updating. The cosmology does not need replacing, but acknowledging that the models need updating does not diminish the significance of what Webb has found. The pressure is real. The gap between prediction and observation is large, and JADES-GS-z14-0 and MoM-z14 are not isolated cases. They are the sharpest examples of a pattern that extends across multiple surveys, multiple redshift bins, and multiple observational techniques. The early universe was brighter, more chemically active, and more structurally developed than the pre-Webb consensus anticipated. Two galaxies confirm that pattern with unprecedented clarity, but they are not the whole pattern. Dozens of other confirmed galaxies between redshift 10 and 13 support the same conclusion. Photometric candidates at even higher redshifts, some awaiting spectroscopic confirmation, suggest the trend may continue deeper into the dark ages. And the pattern does not stop at individual galaxies. The same pressure that bright early galaxies place on formation models is echoed at larger scales, in the chemical enrichment timelines, in the progress of reionization, and in structures far more massive than any single galaxy. The early universe was not only assembling galaxies faster than expected, it was also organizing matter into larger configurations. Concentrations of dark matter and hot gas bound together by gravity into structures that should have taken considerably longer to reach the state in which Webb has now observed them. The individual galaxy story is striking. But when the lens pulls back to reveal the wider landscape of early cosmic structure, the troubling questions multiply. Individual galaxies can be explained away. One spectacularly bright object at the frontier of detectable cosmic time might be a freak, a statistical outlier plucked from the extreme tail of a probability distribution. Two objects might be an unfortunate coincidence, but when multiple independent survey programs, using different instruments, different target fields, and different selection criteria, all converge on the same result, the conversation changes. The question shifts from, how do we explain this particular galaxy, to what is wrong with our baseline expectation for the early universe as a whole? And that is exactly where the James Webb Space Telescope has driven the field. JADES-GS-z14-0 and MoM-z14 are the sharpest individual examples of a broader phenomenon, but they are not the full scope of it. Behind them sits a population of bright, confirmed galaxies, scattered across the first billion years of cosmic history in numbers that the pre-Webb theoretical landscape did not anticipate. The tension is not about one record-breaking object. It is about a systematic mismatch between what the models predicted and what the sky actually contains. The statistical tool astronomers use to quantify this mismatch is the ultraviolet luminosity function, a measurement that describes how many galaxies exist at each level of intrinsic brightness for a given redshift. Before Webb launched, theoretical models and extrapolations from Hubble data predicted that this function would drop steeply at the highest redshifts. Fewer and fewer bright galaxies should have existed as you wound the clock back toward the dark ages, because the universe simply had not had enough time to build massive, luminous structures. The decline was expected to accelerate above redshift 10, and by redshift 13 or 14, the luminosity function was forecast to plummet towards zero. Bright galaxies at those epochs were supposed to be extraordinarily rare or altogether absent. Webb surveys told a different story. The programs introduced earlier, JADES, SEERS, Cosmos Webb, GLASS, Panoramic, each attacked the problem from a different angle. Some prioritized depth, staring at tiny patches of sky for hundreds of hours to reach the faintest objects. Others prioritized area, sweeping across broader regions to capture the brightest and rarest candidates. Still others used the gravitational magnification of massive foreground galaxy clusters to detect objects too faint for direct imaging. The strategies were different. The instrument configurations were different. The analysis pipelines were built by independent teams using independent calibrations, and every single one of them reported the same disquieting result. There were far more bright galaxies at high redshift than anyone had expected. The numbers are not ambiguous. At redshifts above 10, the observed ultraviolet luminosity function exceeds pre-Webb model predictions by factors ranging from roughly 10 to well over 100, depending on the specific brightness range and redshift interval. The decline toward higher redshifts is much shallower than forecast. Instead of a cliff edge where galaxies vanish, the data show a gentle slope, as though the early universe was reluctant to stop producing luminous objects even at ages when the standard timeline barely allowed their existence. Imagine conducting a census of a remote desert region where satellite data suggested a handful of isolated tents, and discovering instead a small city with roads, plumbing, and electrical grids already in place. The individual buildings might each have a plausible explanation, but the collective pattern demands something more systematic. This abundance excess is not driven by photometric candidates alone. The early months of Webb operations did produce a surge of photometric dropout detections that raised concerns about contamination. Low redshift galaxies with unusual dust properties, cool dwarf stars in the Milky Way, and instrumental artifacts could all potentially mimic the color signatures of high redshift objects. But spectroscopic follow-up campaigns systematically addressed those concerns over the course of 2023, 2024, and into 2025. The confirmation rate turned out to be high. Interlopers existed, as expected, but they were a minority. The bulk of the photometric candidates at redshifts between 10 and 14 held up under spectroscopic scrutiny. The galaxies were real, their distances confirmed by emission lines, and Lyman alpha breaks measured with NIRSpec's resolving power. The excess is not a selection artifact. It is a physical feature of the early universe. And the issue extends beyond sheer numbers. The galaxies Webb is finding at extreme redshifts are not just more numerous than expected. Many of them are also more luminous than expected for their cosmic age, more compact and more chemically enriched. The nitrogen signatures in MoM-z14 and the oxygen detection in JADES-GS-z14-0 are particularly striking examples, but they are embedded in a broader pattern of chemical complexity showing up earlier than standard evolutionary models assumed. Multiple galaxies observed by Webb at redshifts between 5 and 11 show anomalous nitrogen-to-oxygen ratios, elevated metallicities for their age, and emission line patterns that suggest dense, efficient star-forming environments unlike anything observed in the nearby universe at comparable scales. The galaxy GN-z11, originally discovered by Hubble and spectroscopically confirmed at redshift 10.6 by Webb, provides one of the clearest illustrations. Its rest-frame ultraviolet spectrum, measured with exquisite sensitivity by NIRSpec, shows nitrogen emission features requiring gas densities exceeding 100,000 electrons per cubic centimeter and nitrogen-to-oxygen ratios far above what standard chemical evolution models predict for its age. The pattern resembles the abundant signatures seen in the Milky Way's ancient globular clusters, the same connection that emerged independently in the MoM-z14 analysis. Across multiple objects at multiple redshifts, the same chemical story keeps surfacing. The early universe was enriching its gas with heavy elements faster and through more concentrated channels than the default models assumed. This chemical pattern is not confined to 2 or 3 headline objects. Webb's spectroscopic campaigns have revealed nitrogen-enriched emission in galaxies spanning a wide redshift range, from objects at redshift 5.55 where dense, chemically stratified gas has been mapped through multiple ionization states, to the most extreme frontiers above redshift 14. At intermediate redshifts between 7 and 10, several galaxies show carbon and nitrogen emission line ratios that require metallicities well above what standard enrichment histories predict for their formation epoch. Some of these objects display spatially compact emission regions, consistent with dense star-forming clumps embedded within larger galactic structures, environments where the enrichment cycle of birth, fusion, death, and recycling could have turned over multiple times in rapid succession. The pattern is not universal. Not every high redshift galaxy shows anomalous abundances. but the fraction that does is higher than pre-Webb models anticipated, and the objects that do show these signatures tend to cluster at the bright, compact end of the early galaxy population, exactly the demographic where rapid, concentrated star formation would be most effective at accelerating chemical evolution. This chemical enrichment timeline connects to another dimension of the emerging tension: reionization. The transition from a neutral to an ionized intergalactic medium is one of the most consequential events in cosmic history. After recombination left the universe filled with neutral hydrogen, the first luminous sources, stars, galaxies, accreting black holes, began producing ultraviolet photons, energetic enough to strip electrons from hydrogen atoms. These ionizing photons carved growing bubbles of transparent ionized gas around each source. Over hundreds of millions of years, the bubbles expanded, overlapped, and eventually merged, completing the reionization of the entire intergalactic medium. By redshift 6, approximately 1 billion years after the Big Bang, the process was largely finished, and the universe was transparent to ultraviolet light once more. The physical texture of this process matters for understanding why Webb's discoveries pressure the timeline. Reionization was not a uniform, simultaneous transition. It was patchy and uneven, driven by the geography of where luminous sources happened to form. Around each bright galaxy or cluster of galaxies, an ionized bubble expanded outward into the surrounding neutral gas at a rate determined by the production rate of ionizing photons and the density of the gas being ionized. A galaxy forming stars vigorously in a moderately dense region might carve a bubble several million light-years across within a few tens of millions of years. A dimmer, more isolated source would produce a smaller bubble. Where galaxies clustered together in overdense regions, their individual bubbles expanded into each other and merged into larger ionized volumes, like separate pockets of warmth in a cold room gradually overlapping until the entire space reaches a uniform temperature. In underdense voids between filaments, where fewer galaxies formed and ionizing photons were scarce, patches of neutral hydrogen persisted longer, the last dark holdouts in an increasingly transparent universe. Think of the process like bubbles forming in a pot of water, approaching a boil. At first, individual bubbles appear at scattered points on the bottom. Each bubble grows, rises, and merges with its neighbors. Eventually, the entire pot is turbulent with interconnected bubbles, and the water transitions fully from calm liquid to a rolling boil. Reionization followed a similar topology, except the bubbles were made of ionized gas expanding through a sea of neutral hydrogen, and the transition took hundreds of millions of years rather than seconds. The spatial distribution of those bubbles, their sizes, overlap regions, and the neutral patches between them is encoded in observational signatures that astronomers are now working to detect directly. Ground-based and space-based radio experiments targeting the 21-centimeter hyperfine transition of neutral hydrogen are attempting to map this patchwork across cosmic time. Instruments like the Hydrogen Epoch of Reionization Array, HERA, and the planned Square Kilometre Array, SKA, aim to detect the statistical signature of neutral hydrogen as it was progressively consumed by expanding ionized bubbles. These experiments have not yet produced definitive detections of the reionization signal, but they are approaching the sensitivity required to do so. When they succeed, the resulting maps will provide an independent test of how early and how rapidly reionization began. The timeline of reionization has been constrained by multiple observational techniques. The optical depth of the cosmic microwave background to electron scattering, measured by the Planck satellite, indicates that reionization was roughly half complete by redshift 8 or 9. Observations of Lyman alpha absorption in the spectra of distant quasars place the tail end of reionization near redshift 6, when the last neutral patches were cleared. Between these constraints, the standard picture assumed that reionization was a gradual process driven primarily by galaxies at redshifts between 6 and 12, with the bulk of the ionizing photon production occurring after redshift 10. Webb's discoveries pressure this timeline from the early end. The abundance of luminous galaxies at redshifts above 10 means that more ionizing photon sources existed during the opening stages of reionization than the standard models assumed. The evidence from MoM-z14 that its immediate surroundings were already partially ionized at redshift 14.44 where models predict nearly 100% neutral gas, suggests that ionized bubbles were forming even earlier than the main reionization window. If galaxies were common enough and luminous enough to begin clearing the neutral fog before redshift 14, the overall reionization process may have started earlier, proceeded faster, or been driven by sources that previous models underweighted. The implications cascade through multiple areas of astrophysics. An earlier start to reionization affects models of the intergalactic medium, changes the predicted absorption signatures in quasar spectra, alters the relationship between galaxy properties and their surrounding environments, and modifies the expected signal in future 21-centimeter experiments designed to map neutral hydrogen during the Dark Ages and cosmic dawn. If the ionized bubbles were larger and more numerous at redshift 14 than models predict, the 21-centimeter signal at that epoch will look different, with larger holes in the neutral hydrogen map and a different statistical power spectrum than current forecasts assume. None of these consequences invalidate the basic reionization framework, but they require recalibration, and that recalibration depends on understanding exactly how many luminous galaxies existed at the earliest epochs and how efficiently they produced and released ionizing radiation. Up to this point, the tension has centered on individual galaxies and the statistical properties of early galaxy populations. But the James Webb Space Telescope has revealed something broader and, in certain respects, even more challenging. The large-scale structural organization of matter in the early universe appears to have been more advanced than the standard hierarchical framework predicted. The evidence for this does not come from a single observation, but from a growing set of discoveries across a range of redshifts, showing that galaxies were not only forming early but also clustering and organizing into larger structures, earlier than expected. At redshifts between 7 and 10, Webb has identified regions where galaxies concentrate in overdensities far exceeding the cosmic average. Some of these appear to be the nascent precursors of galaxy clusters, structures astronomers call protoclusters, loose associations of galaxies and gas that will eventually collapse into the bound, virialized clusters observed in the nearby universe. The significance of finding mature-looking overdensities at these epochs is that the dark matter halos hosting them must have been among the first to reach sufficient mass for large-scale gravitational assembly. The hierarchical model predicts that such structures should be rare at high redshift because the initial density fluctuations that seeded them had not yet had enough time to grow to the required amplitude. Finding them in multiple survey fields suggests either that the initial fluctuations were stronger than assumed in those regions, or that the process of halo growth and galaxy assembly was more efficient than the standard models predict. The most compelling individual case of early structural maturity, however, comes not from the highest redshifts but from an epoch astronomers call cosmic noon, in the form of a galaxy cluster, whose dark matter concentration has become one of the most discussed measurements in recent observational cosmology. XLSSC-122 sits at redshift 1.98. That corresponds to a look-back time of approximately 10.4 billion years, meaning the light Webb collected from this cluster left when the universe was about 3.3 billion years old. In cosmic terms, that is not as early as MoM-z14 or JADES-GS-z14-0. But what makes XLSSC-122 important is not its distance from the Big Bang. It is what the cluster had already become by that point. The cluster was originally identified through its X-ray emission by the European Space Agency's XMM Newton Observatory as part of a wide-area survey called the 25 square degree XXL survey. X-ray emission from galaxy clusters comes from the intracluster medium, an enormous reservoir of gas heated to tens of millions of degrees by the gravitational energy released as the cluster assembled. Detecting this emission confirmed that XLSSC-122 was not just a loose grouping of galaxies, but a genuinely massive, gravitationally bound structure with a deep potential well. Subsequent observations with the Hubble Space Telescope confirmed the cluster's redshift through spectroscopy and revealed that its member galaxies had surprisingly mature stellar populations, collections of old, red stars whose formation ages traced back to when the universe was only approximately 370 million years old. The galaxies inside the cluster were not young, blue, and actively forming stars at a high rate. They looked evolved. They looked old. They looked like galaxies that had already passed through their most vigorous phase and settled into a quieter state, which was unusual for a cluster at such an early cosmic epoch. Then, in August of 2024, Webb's NIRCam observed the cluster in 4 infrared filters. The resulting images transformed the scientific picture, curving around the central region of the cluster. Unmistakable in the deep infrared data, appeared blue-grey arcs of light. These were not features of the cluster itself. They were images of background galaxies lying far behind LSSC-122. Their light bent and stretched into arcs by the immense gravitational field of the cluster's concentrated mass. This phenomenon, gravitational lensing, had been predicted by Einstein's general theory of relativity more than a century earlier. Massive objects curve the geometry of space-time around them, and light from more distant sources follows those curves, producing distorted, magnified, and sometimes multiply image versions of the background objects. Strong lensing, the regime that produces visible arcs and dramatically distorted images, requires a concentration of mass dense enough to significantly bend light paths. Not every galaxy cluster acts as a strong lens. The cluster must have enough mass packed into a sufficiently small volume for the geometric distortion to be severe enough to produce arcs. LSSC-122 produced them, and with that discovery, it became the most distant galaxy cluster ever confirmed to exhibit strong gravitational lensing. The giant arcs enabled a direct measurement of the cluster's internal mass distribution because the shapes, positions, and magnifications of the lensed images are determined by the gravitational field of the foreground mass. By constructing a mathematical model of the cluster's mass profile and fitting it to the observed arc positions, the team led by Kyle Finner was able to measure the radial density profile of the dark matter halo with a precision that X-ray or dynamical methods alone could not achieve. 3 peer-reviewed studies on LSSC-122 were published in the Astrophysical Journal Letters and presented at the 248th meeting of the American Astronomical Society in June of 2026. The results converged on a set of measurements that carry significant implications for the standard model of structure formation. The strong lensing analysis measured the cluster's dark matter profile using a Navarro-Frenk-White model, the standard mathematical description for the density structure of dark matter halos in lambda-CDM cosmology. The best fit concentration parameter, a number that quantifies how centrally concentrated the dark matter is within the halo, came out at 6.3, plus or minus 0.5. This number, on its own, sounds abstract. Its significance becomes clear only when compared to what lambda-CDM simulations predict for a cluster of this mass at this redshift. The standard hierarchical model of structure formation predicts that the most massive dark matter halos assemble late in cosmic history. Smaller halos form first, merge with each other over billions of years, and gradually build up into the massive halos that host galaxy clusters. Because this assembly process is ongoing at high redshift, cluster-scale halos at redshift 2 are expected to be dynamically young, loosely organized, and low in central concentration. Their dark matter has not yet had time to settle into a tightly packed core. Simulations by multiple independent groups, using different numerical codes and cosmological parameters, consistently predict that a halo of XLSSC-122's mass at redshift 1.98 should have a concentration parameter significantly below 6. XLSSC-122's measured concentration of 6.3 sits 3.2 standard deviations above the predictions of every major lambda-CDM simulation tested against the data. The research team fit the observed radial density profile against a variety of published mass concentration relations, mathematical formulas calibrated on large simulated halo populations. None of the standard relations reproduced the observed profile. Each one underestimated the concentration, predicting a more diffuse, less centrally packed dark matter distribution than the data showed. The cluster's core has assembled and condensed faster than the standard model allows for an object of this mass at this cosmic age. It is as though the structural scaffolding that should still have been flexible and loosely assembled had already hardened and set into a rigid, concentrated framework, billions of years ahead of the expected schedule. A companion study used weak gravitational lensing, a subtler version of the technique that relies on the slight statistical distortions of many background galaxy shapes rather than the dramatic arcs of strong lensing, to independently confirm the mass and concentration measurements. Webb's depth and resolution increased the density of usable background galaxies by roughly a factor of 4 compared to earlier Hubble observations, providing tighter constraints on the mass profile out to larger radii. The weak lensing concentration was in statistical agreement with the strong lensing result, reinforcing the conclusion that the anomaly was not an artifact of the modelling technique. A third study focused on the cluster's intracluster light, the faint diffuse glow produced by stars that have been stripped from individual galaxies and now orbit freely within the cluster's gravitational potential. The detection of intracluster light, extending hundreds of kiloparsecs from the brightest cluster galaxy, made XLSSC-122 one of the earliest known clusters in which this phenomenon has been observed. Intracluster light is typically associated with dynamically evolved clusters that have undergone significant gravitational processing, repeated galaxy interactions, tidal stripping events, and mergers that liberate stars from their parent galaxies. Finding it at redshift 1.98 adds to the picture of a cluster that is more structurally mature than its cosmic age should allow. And yet the cluster is not a simple, relaxed system. Multi-wavelength data, including X-ray observations of the hot intracluster gas and radio observations of its broader environment, indicate that XLSSC-122 is undergoing an active merger. It is dynamically disturbed, still assembling, still accreting material from its surroundings. This is not a contradiction. It means the cluster is simultaneously growing through violent merger activity and exhibiting a core concentration that exceeds what the standard model predicts for a system at this stage of its evolution. The question is not whether the cluster is finished forming. It clearly is not. The question is how its dark matter core achieved such a high concentration so early in the assembly process. The total mass of the cluster, estimated from the strong lensing model at approximately 2.6 times 10 to the 14th solar masses, places it firmly in the range of massive galaxy clusters. The mass within the inner 100 kiloparsecs alone is approximately 6.5 times 10 to the 13th solar masses. These are not unusual numbers for galaxy clusters in the nearby universe. What is unusual is encountering a cluster of this mass with this level of core concentration at a redshift where the universe was only 1/3 of its current age. One aspect of XLSSC-122 that deepens its significance is the stellar population ages of its member galaxies. Spectroscopic analysis by Hubble indicated that the stars in the cluster's galaxies appear to have begun forming when the universe was only approximately 370 million years old. That formation epoch overlaps with the same cosmic window in which JADES-GS-z14-0 and MoM-z14 are being observed. The galaxies inside XLSSC-122 may have been among the earliest objects to form in the observable universe, and by redshift 2, they had already aged, reddened, and settled into the evolved configurations typical of galaxies in much older clusters at lower redshifts. The connection between XLSSC-122 and the high redshift galaxy abundance problem is not direct in the sense that one caused the other. The cluster sits at a different redshift, a different cosmic epoch, and a different scale of structure, but the two phenomena share a common thread. Both point toward a universe in which massive structures, whether individual galaxies or gravitationally bound galaxy clusters, assembled and matured earlier and more efficiently than the standard theoretical baseline predicted. The bright galaxies at redshift, 14 challenge models of early star formation and chemical enrichment, XLSSC-122 challenges, models of dark matter halo growth and gravitational assembly. Together, they suggest that the tension is not confined to one narrow corner of astrophysics. It spans multiple scales, multiple epochs, and multiple physical processes. This is what transforms the story from a collection of remarkable individual discoveries into something more systemic. If the only anomaly were a single bright galaxy at redshift 14, the explanation might be straightforward. A rare statistical fluctuation in the initial density field, an exceptionally massive dark matter halo that happened to form early, a lucky alignment of conditions that produced a precocious outlier. but the anomalies are accumulating across scales and across time. Bright galaxies appear too numerous at redshift 10 through 14. Chemical enrichment appears too advanced at those same epochs. Reionization appears to have started earlier than the standard timeline assumed. And at redshift 2, a galaxy cluster shows a dark matter concentration that sits 3.2 standard deviations above the predictions of the leading cosmological simulations. None of these tensions, taken individually, is sufficient to falsify the standard cosmological model. A 3.2 sigma deviation is notable, but falls short of the 5 sigma threshold that physics conventionally requires for a definitive discovery. The galaxy abundance excess might be resolved by adjusting star formation efficiency parameters within existing models. The chemical enrichment puzzle might be explained by unusual stellar populations, extreme mass functions, or dense formation environments that are rare but not physically impossible. The early reionization evidence might reflect local conditions around the most luminous galaxies rather than a global shift in the reionization timeline. But the pattern matters. When multiple independent lines of evidence from different observational programs at different redshifts, using different physical tracers, all point in the same direction, the cumulative weight of the evidence becomes harder to dismiss as coincidence. The direction they point toward is not that the universe is broken or that the Big Bang has been disproven. It is that the early universe was more efficient at assembling complexity than the most widely used pre-Webb models assumed. Stars formed faster, metals accumulated sooner, gas collapsed more readily into the gravitational wells carved by dark matter, and the dark matter itself may have organized into concentrated structures on timescales shorter than the standard hierarchical model comfortably predicts. This does not mean every model is wrong. Some simulations, particularly those that incorporated higher star formation efficiencies at early times, or allowed for non-standard stellar mass functions, came closer to matching the observed galaxy abundances than others. Some formation scenarios that invoked rapid gas accretion in dense early environments or contributions from early accreting black holes reduced the tension for specific objects. The field is not without candidate explanations. What it lacks is a single, unified framework that simultaneously accounts for the galaxy abundance excess, the chemical enrichment timeline, the reionization evidence, and the structural maturity of objects like XL-SSC122, without introducing tensions elsewhere. That framework has not yet emerged, and until it does, the troubling questions remain open. What exactly those questions are, what they mean for the standard model, what the leading candidate explanations actually involve, and where the boundary between legitimate scientific tension and sensationalized overclaim actually falls, those are the questions that remain to be answered. The evidence has been laid out. 2 galaxies at the frontier of cosmic dawn, a population of bright early objects defying the predicted luminosity functions, chemical signatures arriving ahead of schedule, a galaxy cluster with a dark matter core too concentrated for its age. The early universe, it turns out, was not the slow, empty, featureless expanse that the cleanest formation timelines once described. It was already in a hurry. The question now is what, precisely, that hurry tells us about the physics governing the first few 100 million years of cosmic history. There is a version of this story that travels well on the internet. It goes something like this. The James Webb Space Telescope has found galaxies that should not exist. The Big Bang theory is collapsing. Scientists are panicking. Cosmology is broken. Everything you were taught is a lie. The narrative is seductive because it promises a revolution. The exhilarating feeling of watching an established order topple and being among the first to witness the fall. It flatters the audience by implying that they are seeing the truth before the mainstream catches up, and it is almost entirely wrong. The discoveries described in this story are real. The galaxies are real, the measurements are confirmed. The tension between observation and pre-Webb prediction is significant, documented in peer-reviewed literature, and acknowledged by the same astronomers who built the models that are now under pressure. None of that is in dispute, but the gap between the evidence and the sensationalized framing is enormous, and closing that gap honestly is more important than either the comfort of the old models or the thrill of declaring them dead. The early universe produced surprises. The task now is to understand what those surprises actually mean, what they do not mean, and where the boundary between legitimate scientific revision and reckless overclaim actually falls. Start with what the evidence firmly establishes. Two galaxies, JADES-GS-z14-0 and MoM-z14, have been spectroscopically confirmed at redshifts above 14, placing their observed light within the first 300 million years after the Big Bang. Their luminosities, compact sizes, and chemical properties indicate that efficient star formation and at least partial chemical enrichment were already underway, at an epoch when most pre-Webb models predicted very little detectable activity. Multiple independent surveys have confirmed that bright galaxies at redshifts above 10 exist in numbers roughly 100 times higher than those models forecast. At redshift 1.98, the galaxy cluster XLSSC122 exhibits a dark matter core concentration 3.2 standard deviations above the predictions of every major lambda-CD-M simulation tested against it, suggesting that large-scale structural assembly was more advanced at that epoch than the standard hierarchical timeline anticipated. Chemical signatures in multiple high redshift galaxies, including nitrogen-to-carbon ratios far exceeding solar values, point toward enrichment channels that operated faster or through denser formation environments than the default evolutionary models assumed. Evidence from the damping wing of MoM-z14 suggests that local reionization may have started earlier than most models, place the beginning of that global transition. These are the confirmed observations. They are robust, replicated across independent programs, and supported by spectroscopic data at the gold standard level of astronomical distance confirmation. They are not going away. Now consider what these observations do not establish. They do not show that the Big Bang did not happen. The cosmic microwave background, the observed abundance of light elements from primordial nucleosynthesis, the large-scale homogeneity and isotropy of the universe, the measured expansion of space, all of the independent lines of evidence supporting the Big Bang framework remain intact. Nothing Webb has observed contradicts them. The early galaxies exist within the expanding, cooling, structure-forming universe that the Big Bang model describes. They formed from the hydrogen and helium produced in primordial nucleosynthesis. Their light has been redshifted by the same cosmic expansion that the model predicts. The Big Bang is not threatened by bright galaxies at redshift 14. It is the framework within which those galaxies came into being. The observations also do not show that lambda-CD-M cosmology has been falsified. Lambda-CD-M is a specific implementation of Big Bang cosmology that includes cold, dark matter as the dominant form of gravitating matter and a cosmological constant as the driver of accelerating cosmic expansion. It successfully explains the temperature fluctuation pattern of the cosmic microwave background, the large-scale clustering of galaxies, the dynamics of galaxy clusters, and the observed expansion history of the universe measured through supernovae and baryon acoustic oscillations. These successes are not erased by the discovery of bright early galaxies. What is under pressure is not the cosmological model itself, but the astrophysical models layered on top of it. The specific assumptions about how efficiently gas converts into stars within dark matter halos, how the first stellar populations were distributed in mass, how feedback from supernovae and black holes regulated early star formation, and how quickly chemical enrichment could proceed in the densest early environments. This distinction is not a technicality. It is the difference between saying the foundation of a building has cracked and saying a few interior walls need to be repositioned. Both require work. Only one threatens the structure. So, what are the actual leading explanations for the bright early galaxy excess? The first and most widely discussed is enhanced star formation efficiency at early times. In the standard framework, the relationship between a dark matter halo's mass and the number of stars that form within it is described by a function called the star formation efficiency. This function has been calibrated primarily using observations at lower redshifts, from the nearby universe out to redshift 6 or 7, where data are abundant and models are well tested. The calibration assumes that the efficiency does not change dramatically with cosmic time. Gas falls into halos, cools, fragments, and forms stars at rates governed by local conditions such as gas density, metallicity, turbulence, and the energy injected back into the surrounding gas by stellar winds, supernovae, and accreting black holes. These feedback processes are thought to limit how quickly a halo can turn its gas into stars, preventing the efficiency from ever approaching 100%. But at the earliest cosmic times, conditions may have been different in ways that favor higher efficiency. Gas in the first dark matter halos was predominantly primordial hydrogen and helium, with lower metallicity and therefore less efficient radiative cooling through metal emission lines. However, the halos themselves were denser at fixed mass compared to later epochs, because the universe was physically smaller and matter was packed more tightly. The gas flowing into these halos may have been colder relative to the halo's virial temperature, falling inward in dense, coherent streams, rather than heating to a diffuse shock-supported atmosphere. This mode of gas accretion, sometimes called cold flow accretion, could have delivered raw material to the centers of halos more efficiently and more rapidly than the smooth, shock-heated accretion that dominates at later times. If the gas arrived colder and denser, it could have collapsed and formed stars with less delay and less energy lost to heating. Think of star formation efficiency at lower redshifts like a thermostat set to a single comfortable temperature. The gas heats up, cools down, and the feedback processes keep it regulated within a narrow range. At the highest redshifts, the thermostat may not have been installed yet. The first halos may have operated more like unregulated furnaces, converting gas into stars at rates closer to the theoretical maximum before feedback had time to establish itself. Several recent modelling efforts have demonstrated that allowing the low mass slope of the star formation efficiency function to evolve toward higher values at early times can bring the predicted ultraviolet luminosity functions into much closer agreement with the observed Webb data, without requiring any modification to the underlying lambda-CDM cosmology. The adjustment is not small, but it is physically motivated and consistent with what we know about early gas dynamics. The second explanation involves the stellar initial mass function, the statistical distribution of masses among newly formed stars. In the nearby universe, this distribution follows a well-characterized pattern: many low-mass stars, fewer intermediate mass stars, and a steep decline toward the highest masses. This distribution, known informally as the Salpeter or Kruper initial mass function depending on the specific parameterization, has been calibrated through observations of star-forming regions in the Milky Way and nearby galaxies, but there is no fundamental reason to assume it was identical in the very first star-forming environments. If the earliest stellar populations formed with a top-heavy distribution, meaning a higher proportion of massive stars relative to low-mass ones, the resulting galaxies would produce far more ultraviolet light per unit of stellar mass. A galaxy with a top-heavy initial mass function could appear as luminous as a galaxy with several times more total stellar mass formed under a normal distribution. This would make early galaxies look brighter without requiring them to have assembled more mass, reducing the tension with formation timelines. The challenge with this explanation is that it is difficult to test directly at high redshift. The initial mass function cannot be measured star by star in a galaxy 13 billion light-years away. Its effects can only be inferred through indirect tracers, emission line ratios, luminosity to mass comparisons, and chemical abundance patterns, all of which depend on modelling assumptions. A top-heavy initial mass function at early times is plausible, physically motivated by the higher temperatures and lower metallicities of primordial gas, and consistent with some of the observed properties of the brightest high redshift galaxies, but it has not been confirmed as the dominant explanation. The third candidate is bursty star formation, and it deserves more attention than it often receives because it operates through a fundamentally different mechanism than the first two explanations. Rather than forming stars at a steady, continuous rate, early galaxies may have experienced intense, short-lived episodes of star creation, separated by quieter intervals. The physical driver of this variability lies in the feedback loop between star formation and the gas reservoir that fuels it. When a dense pocket of gas collapses and ignites a burst of star formation, the resulting massive stars pour energy back into the surrounding medium through radiation pressure, stellar winds, and eventually supernova explosions. This energy heats and disperses the nearby gas, temporarily shutting down further star formation in that region. The galaxy dims, but gravity does not stop working. Over time, the expelled gas cools, falls back into the gravitational well, and accumulates until conditions again favor collapse. Another burst ignites. The galaxy brightens dramatically, then fades again as the new generation of massive stars blows the gas out once more. This cycle of compression, burst, expulsion, cooling, and reaccretion creates a flickering pattern of luminosity. During a burst, a galaxy's ultraviolet output can spike by factors of 10 or more as millions of hot young stars blaze simultaneously. Between bursts, the output drops sharply as the massive stars die and the gas has not yet reaccumulated for the next episode. The duty cycle, the fraction of time a galaxy spends in its bright phase versus its dim phase, determines how many galaxies appear luminous in any given snapshot. If the duty cycle is short, say 10 or 20%, then at any given moment only a small fraction of all galaxies at that redshift are caught mid-burst. But those galaxies are so bright during the burst that they dominate the luminosity function at the high brightness end. Imagine a dark room filled with 100 strobe lights, each flashing independently at random intervals. At any given instant, only 10 or 20 might be on, but a photographer taking a long exposure image would record all 100 positions as though they were constantly illuminated. The ultraviolet luminosity function works similarly. Surveys accumulate detections over large volumes of space, catching different galaxies at different points in their burst cycles. If bursts are common, intense, and short, the resulting luminosity function appears inflated at the bright end, not because more galaxies exist, but because the ones that do exist spend a fraction of their time at extreme luminosities that steady-state models never produce. Several theoretical groups have explored this mechanism quantitatively and found that it can explain a significant fraction of the observed discrepancy, particularly when combined with modest increases in star formation efficiency. The stochastic variability does not replace enhanced efficiency as an explanation. It works alongside it. A galaxy with moderately elevated efficiency that also experiences bursty episodes can achieve peak luminosities far exceeding what either mechanism alone would produce. The combination is more powerful than either ingredient in isolation, and it arises naturally from the physics of gas dynamics and stellar feedback in small, dense, early halos. A fourth contributing factor is reduced dust obscuration. Dust absorbs ultraviolet light and re-emits it at far infrared wavelengths. In the nearby universe, a significant fraction of star formation is hidden by dust, and corrections for dust obscuration are routinely applied when estimating galaxy luminosities and star formation rates. At the highest redshifts, galaxies are expected to contain less dust because fewer generations of stars have produced and dispersed the solid particles that constitute interstellar dust. MoM-z14's steep ultraviolet spectral slope directly confirms negligible dust attenuation in that object. If early galaxies were systematically less dusty than their lower redshift counterparts, their ultraviolet light would escape more completely, making them appear brighter at fixed star formation rate. This is not an exotic explanation. It is a natural consequence of the expected chemical state of early galaxies, and it contributes to the observed excess without requiring any modification to the underlying formation physics. A fifth possibility involves contributions from active galactic nuclei, accreting supermassive black holes at the centers of early galaxies. A black hole rapidly consuming surrounding gas can produce luminosities that rival or exceed the combined stellar output of an entire galaxy. If early galaxies hosted active black holes that contributed significantly to their total ultraviolet emission, the inferred stellar masses and star formation rates would be lower than pure stellar models suggest. However, for several of the key high redshift galaxies, including JADES-GS-z14-0, the spatially resolved nature of the emission and the absence of characteristic spectral signatures of black hole accretion argue against active galactic nuclei as the primary luminosity source. Black hole contributions may play a role in some objects, but they do not appear to dominate the population as a whole. The crucial insight from recent theoretical work is that no single one of these explanations needs to bear the full weight of the discrepancy. Combinations are not only permitted, but expected. A modest increase in star formation efficiency at early times, combined with a slightly top-heavy initial mass function in the densest environments, reduced dust obscuration in primordial gas, and stochastic variability in star formation histories, can together account for the bulk of the observed excess without requiring any departure from lambda CDM cosmology. Several independent modeling efforts published in 2025 and 2026 have demonstrated this quantitatively, showing that the observed luminosity functions from redshift 4 through 16 can be reproduced within the standard framework once these physically motivated adjustments are applied. The models are not settled. Different groups emphasize different mechanisms. The relative contributions of each factor remain actively debated. But the overall message is consistent. The early galaxy abundance problem has candidate solutions within conventional physics, and the most successful solutions involve refining astrophysical assumptions rather than abandoning cosmological ones. The nitrogen enrichment puzzle sits in a somewhat different category. Enhanced star formation efficiency and stochastic variability can explain why early galaxies are brighter and more numerous than expected. They do not, on their own, explain why the nitrogen-to-carbon ratio in MoM-z14 exceeds solar values by more than a factor of 10 within 280 million years of the Big Bang. That requires an enrichment channel that is both fast and chemically specific. The leading interpretation connects the nitrogen excess to the possible presence of very massive or supermassive stars in dense early stellar clusters. Stars with masses of several hundred to several thousand solar masses, if they existed, would have burned hydrogen through the CNO cycle at extreme rates, converting pre-existing carbon and oxygen into nitrogen far more efficiently than normal stellar populations. These hypothetical objects, which may overlap with or be related to population 3 stars, would have had lifetimes measured in millions of years or less, enriching their surrounding gas with nitrogen before dying in catastrophic explosions or collapses. The abundance pattern produced by such stars closely matches what is observed not only in MoM-z14, but also in the Milky Way's ancient globular clusters, where light element anomalies, including elevated nitrogen, have been documented for decades without a fully satisfying explanation. If the early universe hosted dense stellar nurseries where supermassive stars formed, lived, and died within the first few 100 million years, those nurseries could be the progenitors of the globular clusters that survive today as the oldest bound stellar structures in nearby galaxies. This would mean that Webb, by observing MoM-z14, is witnessing the formation environments of objects that astronomers have studied in the Milky Way for over a century. Finding a prodigy who learned the violin in 6 months is extraordinary, but it does not require rewriting the laws of acoustics. It requires understanding the specific conditions, the early exposure, the intensive practice, the unusual talent that made the accelerated mastery possible. The nitrogen in MoM-z14 demands a similarly specific explanation, not a violation of chemistry, but a set of conditions: dense gas, massive stars, rapid cycling, that compressed a normally slow process into a narrow window. This interpretation is suggestive rather than proven. The data are consistent with it, but other possibilities remain, including contributions from rapidly rotating massive stars, Wolf-Rayet stars with strong nitrogen-enriched winds, or binary star interactions that could alter surface abundances before material is ejected into the interstellar medium. Disentangling these mechanisms will require deeper spectroscopic observations of more galaxies at comparable redshifts, combined with improved theoretical models of nucleosynthesis in extreme environments. The nitrogen puzzle is not closed. It is one of the most active areas of investigation in high redshift astrophysics. The structural tension raised by XLSSC-122 is also ongoing. A 3.2 sigma discrepancy between the observed dark matter concentration and the predictions of major simulations is statistically significant, but not yet at the 5 sigma threshold conventionally required for a definitive result in physics. It is possible that XLSSC-122 is a genuine outlier within the expected distribution, a rare but statistically permissible fluctuation in halo properties. The probability of finding such an outlier by chance is low, less than about 1 in 1,000, but not 0. Enlarging the sample of high redshift clusters with strong lensing measurements will be essential for determining whether XLSSC-122 is an isolated anomaly or the tip of a broader pattern. If multiple clusters at comparable redshifts show similarly elevated concentrations, the case for systematic revision of structure formation models will strengthen considerably. If XLSSC-122 remains a lone outlier, the standard framework may absorb it as a statistical fluctuation without fundamental modification. What the scientific community is grappling with is not a single smoking gun, but a convergence of mild to moderate tensions across multiple observational fronts. No individual result is strong enough to overturn the standard model on its own, but the fact that bright early galaxies, rapid chemical enrichment, early reionization signatures, and concentrated early cluster structure all point in the same direction, toward a universe that assembled complexity faster than the default expectations assumed, creates a cumulative pressure that demands serious engagement. The responsible scientific posture is neither panic nor dismissal. The models are under revision, not under collapse. The Lambda-CDM cosmological framework remains the most successful description of the large-scale universe ever constructed. Its foundational components, general relativity, cold dark matter, a cosmological constant, and the initial conditions seeded by cosmic inflation, continue to pass observational tests across a vast range of scales and epochs. What is being adjusted are the astrophysical recipes built on top of that foundation. How stars form within dark matter halos, how feedback regulates gas consumption, how the first stellar populations were distributed in mass and density, and how quickly chemical enrichment could proceed under conditions unlike anything observed in the nearby universe. These are not minor adjustments, but they are adjustments to specific model ingredients rather than demolitions of the underlying architecture, and the adjustments are being tested. The next generation of observational campaigns is designed specifically to discriminate between the candidate explanations and determine which combination of mechanisms best accounts for what Webb has revealed. Webb itself is far from finished. Its primary mirror has not degraded. Its instruments continue to operate at or near their designed sensitivities. Future observation cycles will target additional high redshift candidates for spectroscopic confirmation, pushing the statistical sample of confirmed galaxies above redshift 12 from the current handful into the dozens. Larger samples will tighten the luminosity function measurements at the highest redshifts, distinguishing between models that invoke enhanced star formation efficiency and those that rely more heavily on bursty variability or top-heavy mass functions. Deeper spectroscopy of already confirmed galaxies will refine chemical abundance measurements, testing whether the nitrogen enrichment pattern in MoM-z14 is typical of the brightest early objects or an outlier even among its peers. Webb will also continue surveying galaxy clusters at high redshift, building the statistical sample needed to determine whether XLSSC-122's concentration is anomalous or representative. Beyond Webb, the Nancy Grace Roman Space Telescope, scheduled for launch, will transform the statistical landscape of high redshift galaxy science. Roman's wide-field infrared survey capability will cover areas of the sky roughly 200 times larger than Webb's deepest fields, discovering thousands of high redshift galaxy candidates across cosmic volumes far exceeding what any current survey has mapped. While Roman lacks Webb's spectroscopic sensitivity and spatial resolution for individual faint targets, its enormous survey area will provide the population statistics needed to measure the bright end of the luminosity function with unprecedented precision. If bright early galaxies are as common as Webb's deep pencil beam surveys suggest, Roman will confirm it across statistically independent regions of the sky, removing any lingering concern that the excess is driven by cosmic variance. The possibility that Webb happened to observe unusually overdense patches of the early universe. On the ground, the extremely large telescope and its counterparts in the next generation of 30-meter class observatories will bring spectroscopic resolving power that surpasses even Webb's capabilities for the brightest targets. These instruments will be able to measure chemical abundances in high redshift galaxies with sufficient precision to distinguish between the nitrogen production channels that are currently degenerate in the data. If the nitrogen enrichment in MoM-z14 was produced by supermassive stars in dense proto-globular cluster environments, the detailed abundance patterns, the ratios of nitrogen to oxygen, carbon to oxygen, and heavier elements relative to hydrogen will follow a specific signature that can be separated from the patterns produced by rotating massive stars or binary interactions. The extremely large telescope's adaptive optics systems will also resolve the internal structure of bright, high redshift galaxies, determining whether their compact morphologies reflect genuinely tiny physical sizes or whether substructure exists that Webb's resolution cannot separate. Radio astronomy will contribute an entirely different observational window. The 21-centimeter experiments now approaching operational sensitivity, including the hydrogen epoch of reionization array and the planned square-kilometer array, will map the distribution of neutral hydrogen during the cosmic dark ages and the epoch of reionization. These maps will provide an independent constraint on when and how quickly the intergalactic medium transitioned from neutral to ionized. If the evidence from MoM-z14's weak damping wing is correct, and ionized bubbles were already forming at redshift 14, those bubbles should appear as holes in the 21-centimeter signal at the corresponding frequencies. A detection of early ionized regions at redshifts above 13 would corroborate the galaxy-based evidence and confirm that the opening act of reionization occurred earlier than the pre-Webb consensus assumed. A non-detection, conversely, would suggest that the ionization around MoM-z14 was an isolated local phenomenon rather than the beginning of a widespread transition. Each of these observational programs attacks the problem from a different angle. Together, they will determine whether the early galaxy abundance excess is explained entirely by enhanced astrophysical efficiency within the standard cosmological framework, or whether the tensions point towards something deeper, a modification of dark matter physics, an adjustment to the initial conditions set by cosmic inflation, or a revision of how gravitational structure grows during the first billion years. The answer is not yet known, but the tools to find it either exist now or are being built. And here is where the story reaches something worth pausing over. The sensationalized version of these discoveries asks you to feel thrilled that science is wrong, that the establishment has been humbled, that the old ideas are crumbling. The more honest version asks you to feel something different and, in its own way, more profound. The early universe was not the empty, silent, structureless void that the simplest timelines described. It was already doing things, making stars, building metals, concentrating dark matter, clearing ionized pathways through neutral hydrogen fog, assembling compact, luminous, chemically complex galaxies within a window of cosmic time so narrow that it barely separates the release of the cosmic microwave background from the epoch we are now observing. The darkness after the Big Bang did not stay dark for long. Something in the physics of gas collapse, dark matter assembly, and stellar ignition operated more efficiently in those early conditions than the models calibrated on later epochs had predicted. The first few 100 million years of cosmic history were not a slow preamble. They were a rush. Stars formed in dense clusters. Massive objects burned through hydrogen at extraordinary rates, producing elements that should have taken far longer to appear. Compact galaxies lit up across the sky in numbers that dwarfed the forecasts, and massive dark matter halos began concentrating their cores into structures that would not have looked out of place billions of years later. None of this means that scientists were foolish or incompetent for building the models that are now being revised. Those models were built on the best data available, using physically motivated assumptions that had been tested against every observation that existed before Webb launched. They worked extraordinarily well for the epochs and objects they were designed to describe. The failure, if it can be called that, was in extrapolation, in assuming that the processes governing galaxy formation at redshifts 6 through 10 could be smoothly extended to redshifts 12, 13, and 14 without encountering new physical regimes or unexpected efficiencies. That assumption was reasonable. It turned out to be incomplete. Science corrects itself not because it is infallible, but because it treats its own assumptions as provisional, subject to revision when new data arrive. The new data have arrived. The revision is underway. What James Webb has given astronomers is not a catastrophe. It is a frontier. The first few 100 million years of cosmic history, long treated as a mostly theoretical epoch accessible only through models and extrapolation, are now an observational science. Real galaxies with real spectra and real chemical signatures are being studied at redshifts that were unreachable barely 4 years ago. Every new confirmation adds detail to a picture that is becoming richer, stranger, and more demanding of explanation. The early universe is no longer a blank page. It is a page covered in handwriting that astronomers are only beginning to learn to read, like a partially decoded manuscript whose grammar is becoming clearer with every newly translated line, even as whole paragraphs remain mysterious. The unsettling part of this story is not that the universe is broken, it is that the universe was already becoming complicated when it was barely old enough to contain anything at all. The cosmic dark ages may have been shorter than assumed. The first stars may have been more massive and more chemically productive than the simplest models predicted. The first galaxies may have formed through processes: cold gas accretion, dense cluster formation, rapid stellar cycling, that were more vigorous than anything observed in the modern universe. And the first large-scale structures may have assembled their dark matter scaffolding with an efficiency that the standard hierarchical model, despite its many successes, did not fully anticipate. The troubling questions are not about whether the universe exists, or whether the Big Bang happened, or whether physics works. They are about tempo. How fast could the universe go from featureless darkness to structured, luminous, chemically active complexity? The answer, written in infrared light that has been travelling for over 13 billion years, is faster than we thought. Perhaps much faster, and every photon that arrives from that distant epoch carries another line of evidence, another constraint, another piece of a puzzle that is being assembled in real time by the same species that, on one small planet orbiting one ordinary star, learned to build a telescope and point it at the edge of time. The darkness after the Big Bang did not last. The universe was already in a hurry, assembling its first stars, its first metals, its first galaxies, and its first massive structures with a speed that the old timelines could not accommodate. James Webb has not broken cosmology. It has opened a window into an epoch where the cosmos was doing more, sooner, than anyone had the evidence to expect. The early chapters of cosmic history are being rewritten, not because the old story was a lie, but because the universe kept better records than we knew how to read. Those records are arriving now, carried across 13 billion years of expanding space, and they carry a message that is equal parts humbling and astonishing. The first light after the darkness was not a faint, tentative flicker. It was a blaze, and we are only beginning to understand how it was lit.